Aloha and welcome, or hopefully welcome back to another episode of the Reliability Matters podcast. For those of you who are counting, this is episode number 166. This episode is a little different than my normal episodes in two ways. First, I didn't record it in my normal studio. In fact, I'm not in my normal studio. I recorded it at the SMTA Pan-Pacific Strategic Electronics Symposium, affectionately known as PanPac, in beautiful Maui, Hawaii. Each year I record a Reliability Matters podcast here at PanPac. Normally the format of the show is I ask questions and my guests provide answers. On this episode, however, I decided to let my guests do all of the talking. The theme of this episode is electronics, down memory lane, and a vision for the future. My three guests on this episode will share their view of the history of electronics from three different perspectives. And who are my guests? My guests are Dr. Ron Lasky from Dartmouth College, Dr. John Evans and Dr. Tom Duval, both from Auburn University. They'll share their perspectives on the history of the electronics industry in presentation format. For those of you who may be listening to this podcast on your phone, you may want to consider viewing this particular episode on the Reliability Matters YouTube channel. Each of my three guests prepared fascinating presentations, including many historical photographs, which I am confident you will find fascinating. So, sit back, pour yourself a Mai Tai, and let's take a trip down memory lane on tropical Maui, Hawaii.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
So I wear my Dartmouth hat a lot, and often people stop and say, "Are you an alumnus of Dartmouth?" I say, "No, I'm a professor." And they'll look at me and they'll say, "Still?" And that hurts a little bit. But it's fun, and the students are great, and they seem to like me a little bit, so I'm going to keep doing it. Okay, so I just click this, I guess, huh? There we go. Okay. Make sure the laser pointer works. Okay. So this was kind of fun for me because I put a career in at IBM, and a lot of electronics evolution I saw. And so this will be a little bit about that, but we'll even go back a little bit before. It's probably one of these things that's obvious that we never think about. As some of our physicist friends say, the electron is the most useful thing in physics. And electricity really defines modernity. And it all started happening about the same time. But in 1870, there was no light pollution, because there were very little, because there wasn't really any electric lights. No man-made electromagnetic radiation. Life expectancy in the U.S. was about 40 years. You know, people talk about the good old days, but they weren't really that good. And Edison started producing the light bulb, mass producing it in about 1879, and the telephone was in about the same period of time. And so by about 1900, modernity began with AC electricity to homes. Edison's DC lost out. We didn't really have electronics until the invention of the vacuum tube, which was invented in 1906 by Lee DeForest, and there's a model of it. And it was the ability to amplify weak signals, and that enabled radio. By the 1930s, radio became a mainstream, and it was in almost everybody's home. And I remember reading some about during the Depression when people lost their jobs and everything. Someone said people would do without food to have a radio. It was became part of the culture that after dinner, you know, especially in places where there wasn't a lot of better entertainment, maybe in the farm way out in Nebraska, that people would sit around the radio at night and listen to shows like Gangbusters and Jack Benny and so forth. And it enabled the fireside chats that FDR had about during World War II to inform the public how the war effort was going. By the late 1940s through the early 1950s, ENIAC, and I think we've already seen a few photos of this in other presentations today. I have a little more information. It took 175 kilowatts of electricity to run it. That's enough for about 100 homes. And 18,000 vacuum tubes And for those of us, the very few of us in the audience that can remember vacuum tube TVs, with that many vacuum tubes, you had one burning out about every 2 hours. And so they developed a way to have a field replaceable unit, and with better vacuum tubes, they improved it to only having a vacuum tube fail about every few days. It performed, and this is what I think is really interesting, it performed 500 flops, 500. The latest iPhone performs 1 trillion flops. 1 trillion flops, and just to keep that in perspective. And this cost, in today's dollars, about $8 million and 500 flops, and for a $1,000 iPhone, or less even, today we can get 1 trillion flops. So the first transistor, I think we've seen this too in some previous talks, was invented in Bell Labs in 1947. There are the three inventors. And by the mid or late 1950s through the 60s, we had the transistor radio, and with such classic songs some of us here used to listen to on these, Transistor Sister, if some of you may remember that one. So this is part of my world. I actually remember this computer when I was in community college. So this was in the mid 1960s through the early 70s. It was one of the first computers to have discrete transistors. Before this, it was vacuum tubes. And I wasn't quite at IBM yet, but I remember hearing stories that the CEO of IBM, Thomas Watson, at some point in time said, I will not allow any patent in the company that uses vacuum tubes. They have to be transistors. And this was about this era. I was a little surprised, so this cost about $1 million in today's money, that it was really only about the speed of the ENIAC, hundreds of flops. It was made especially for scientific calculations, and it had 20K of memory, $1 million. So one of the big breakthroughs in the history of IBM was the announcement of what was called SLT, Solid Logic Technology. And they were able to, for the first time on a little module, put little slivers of silicon and some resistive materials, and have in each one of these little components several circuits. This was, at the time, unheralded, and it was a bet your company type of deal, costing, in today's dollars, billions and billions of dollars by IBM. The largest computer they sold with this technology, and you see the tremendous improvement, was up to 2 million flops. But again, keep this in perspective. That's about 1/500th the speed of it's many millions of times, 500,000 times the speed of your smartphone. It had 2 meg of memory, and it cost about $55 million in today's money. By 1970, and this is when I started working at IBM, it was the first computer to use integrated circuits that IBM sold, and it was up to about 5 million flops, and each IC, each integrated circuit, had 20 to 100 circuits, cost about $75 million in today's dollars. And this was the premium computer in the series. You could buy lower performance for lower dollars. So it was about, so it cost about $75 million. It had about 3 meg of memory. So this was the first IBM PC I bought. It was about $2,500 in 1986. So about 6K today. 100K flops, 10 meg hard drive, 512 RAM, and compared to a new Lenovo computer, about 3 teraflops today. 16 gig of RAM, 1 terabyte hard drive for less than $1,000. So in the commercial world, again, some of us here may pause to think, hey, I remember having a TV like that at home. I actually remember before my parents had a TV, but when we first got one, it was like this, black and white, not color, in the mid-60s, had vacuum tubes. But again, to us, it was a miracle. When I was young, on my street of 50 houses, when I was like 5 years old, there were only 2 TVs. And so 1980s to today, and again, these are other things we can fail to think about. The Sony Walkman was one of the first real personalized electronics. You had a memory, you had a cassette, and you could play a cassette's worth of songs. And it taught us how to miniaturize to the point also that we got, and I remember I was at IBM, we were studying how people made cameras because they were so good at miniaturization, and we're trying to see if we could be as good. So in looking at cameras, this is a 1988 less than 0.4 megapixel camera, and today we can get 44 megapixel anti-shake for $40. I like this one. It shows us the advance of technology and size. This is a walkie-talkie that would be used in the Korean War. It was vacuum tubes, had about 5 to 10 circuits. Here's a 1965 transistor radio with about 10 to 20 circuits. And here's today's smartphone with over 1 billion circuits. This is one we chuckle when we see, but when this movie came out with Michael Douglas, this was like the hottest thing to have this because it was the only mobile phone around, and it cost $4,000 in the money of that era. So what that'd be more than $10,000 today. And this is something I'm most proud of. I spent a lot of time. I won't claim this to be perfect, but this is the cost of computing power as a function of time, starting at about 1980, and this is for a megaflop. How much a megaflop costs? You know, we're in the thousands of dollars, going down to fractions of a penny for a megaflop. And this is also one for memory. And I have to give credit to this and the idea from a guy named Penzias, Arno Penzias, who was a co-discoverer of the microwave background for the Big Bang. I was at a conference where he spoke 20 years ago, and he said in 1970, a meg of memory cost the amount of money of a small apartment building in New Jersey, $1 million. Today, a meg of memory would not pay for the hinge and a door in the apartment. This is 1995. Today, a meg of memory, you can't get a unit of money that small. When you look at this this chart right here. So a meg of memory is much, much less than a penny. So electronics, in a sense, defines modernity, and there's been a stunning cost reduction in computing power and memory to enable today's electronics. And I want to close with one thing. We're all enamored with computing power and how awesome it is, and it's certainly true. But really, if we think about it, inexpensive memory is profoundly important to the devices we have. You really need to have a lot of memory in a small package to have all the electronics perform as they do. So thank you for your attention. And next up is John.
All right, you guys okay? Here we are, I guess. So this was kind of an interesting thing. Ron and I were meeting in September, I guess, when had this idea for the paper. It was going to be a paper, and then to turn the podcast and all that. I think we need to go back and figure out how to actually do a real overall history discussion of electronics design and manufacturing kind of collectively, because as I got through this, it actually turned out to be something that would probably be very valuable. So my presentation, because it's a little bit short here of time, is discussing from my perspective what I saw and things we're doing in electronics that are mostly in complex systems, and automotive was my background. I was technology manager for Chrysler Electronics. And so that area was something that I did work on, research on, also, et cetera, and kind of shows you the complexity of electronics in today's cars and in the future of this as well. Some of you may have a vehicle that looks something like this, that would be 50, 60, 70 years old or whatever, back in the day, where the electronics looks like what you get in a Happy Meal toy now, with the little phenolic board and all the through hole and all that. So real simple stuff. That's not what automotive electronics or complex system electronics are today. A little bit of background in manufacturing. Part of the discussion here of doing a little history was because we have so many new people from different perspectives coming in for this conference now that may not have actually done surface mount technology, for example. So surface mount was probably the big change in electronics that'll let it go to really ramp up massive volume, right? Because we could use double sides of the boards, the packaging got a lot smaller, you could do all sorts of creative stuff, and then that led us to, even today. But the move to using both sides of the board from through-hole technology here today, which, can
can't remember, is it Marcus? Somebody was talking about the other day, talking about the military still using a lot of the of through-hole tops technology, and then going into surface mount. That change really made the big difference in electronics for the volume. If you're not familiar with what an automotive controller, this is one we had in the 90s. Pretty complex. I was giving a presentation to Dan Golden, who was head of NASA one time, and I said, I know you guys have a tough environment or whatever, and he punched me in the chest. He goes, you have the hardest environment in the world. His point was, he goes, you have to make it work at pennies. At NASA, we could gold plate or use exotic metals or whatever, but in the automotive world, every penny counts. So it is even harder than it is in NASA or other systems. But this is a complex system back in the 90s, and it just keeps building from that. Through hole all the way to flip chip technology was a transition between the 70s to 2010 or so in automotive and other complex systems electronics. You can see all sorts of changes that most of us know, and going to very grid array packages, which I'll show you a little bit more in a minute, to optical systems, to stack systems, and all. All of this is part of the complexity of new systems in electronics and the move in different manufacturing. And it will be part of the future as we think about how we're going to get to the next generation electronics modules and things. This is the first multi-chip module and the first ball grid array package in the world under the hood of the car. And this came out of a research project back in the 90s that we were doing with IBM and Allied Signal and a few other companies. Delphi was involved with this. And we ended up, a supplier for this on the bottom left was Motorola, but we entertained, is how we know our old buddy IBM Chuck here, was the IBM cells. And I almost got that business back in the day because we really liked what IBM brought to the table for this, but ended up with Motorola as the supplier. But a lot of the work here, cross sections and modeling and all, was how we started doing a lot of work with Auburn University when I was at Chrysler. This was the core piece program that actually evolved into the CAVE program at Auburn. Those of you that mostly know CAVE, Pradeep is here, been director for 15 plus years or whatever. This was the program that led to the next step where Wayne Johnson, if you know him and all, we rolled the CAVE program out. So that's a little bit of a history from that. And then if you think about the complexity of future modules, this gets into the 2010 or 15 where they're going to Megatronics controllers. Interesting thing, Mike, you had in your presentation yesterday about the BMW electric a half step back, and similar kind of issues happening in the non-electric vehicles on transmission type of stuff there. So a lot of challenges to be able to do that. Memory devices stack all come into play with this as we evolved, and now we start getting into 2020 and on, and real complex systems in electronics for automotive. I don't know if you have thought about this, but when you buy a car, that's most people's biggest electronics purchase. It's $5,000, $6,000, $7,000, $8,000, up $10,000 electronic in the car. And so developing that work is really difficult to do. If you look at the future of this, where we're doing everything with electronics, everything autonomous, electric vehicles and all this, all of this is changing the dynamics of the car and making the complexity even worse. So here's kind of a future of what it is. You look under the hood, it looks all nice and normal, carpet and wheels and stuff, but if you start pulling panels together, you see electronics all over the place in a car. Then you start thinking about the next generation as we get to AI and how we manufacture, package, and deliver this complexity is a real challenge. How do we actually go from the very difficult modules they currently have to this AI-generated world of really, really nasty electronics? And will it be a situation where it evolves back to there's some creative ideas out there in packaging that makes it go back to a simpler time of assembly, but with all the high tech involved with the devices? So this is a bit an interesting thing to see how this evolves over the course of time. This is IBM 50s. Ron shows something similar to this in the computers, and then on the right, quantum electronic systems. And then we'll have quantum devices, hopefully, in the next 10, 15 years. And I mean, who knows? So this is the kind of thing that we have to figure out. How do we go to the next generation of electronics and evolve like we did for the last 60 or 70 years? So with that, I'm going to turn that over to Dr. Duval, who is a lean expert. I've known him for 30 plus years or so. And he is a world-renowned lean manufacturing expert. So he can talk more about the manufacturing process.
For those out in the audience, I know sometimes we talk about real world. I'm just another real world guy that somehow ended up at the university. So I spent 31 years with Chrysler, last 15 in the assembly plant north of Detroit, building a four-door sedan and a convertible every 51 seconds. And then went to Continental Motors, building general aviation piston engines for Continental. For 3 years, I left there as vice president of manufacturing. So that's 34 years. I've been with Auburn 15. I know I don't look that old. Thank you for saying that. But anyway, that's a lot of years. So what I want to talk about is the history of Toyota production system, which I think is critically important for people, a lot of the industry people I work with, that they understand this background. So when we go through it, if they still have the attitude, I don't know if this is for us, it means there's no hope for them, because it's a proven reality, and the data and the information and the history tells you that. So I like to go through that. And so I'm trying to teach a course in lean in 10 minutes. So I'm going to go through the lean house. That'll help. And talk about how all of our systems are full of waste. No matter how good you are, there's tons of waste in all systems. So how do we convert that? And just-in-time material pull versus push, what that is. That's where most manufacturers never move to that level. It's very difficult to do. And lead time, that should be the primary metric of every organization. I'll tell my students, kind of tongue-in-cheek, that I would get rid of every metric in the organization and just measure lead time. Why? Because it drives everything. And if we do that and we'll focus on that and we remove the lead time from the system, we will get better of all aspects of the business. So what is lead time? And then finally, if we're looking at how we're going to implement lean systems, what kind of a sequence of implementation would we follow? Because there's a lot of questions about that. How do we start with this? How do we develop a lean system? So a little bit of the history. I think we all know this person. I won't name his name. He's standing there by the Eiffel Tower, and this is 1940. Scary, right? Scary time. So that prompted the auto industry to start building the war machine. And this is Detroit, early 1940s, and this is tank production at Chrysler, Centerline Road, 10 Mile in Detroit, if you know the area. And Roosevelt referred to Detroit as the arsenal of democracy, and this was an article in Time magazine, how Detroit won the war, right? And then in Ypsilanti, Michigan, which I could see the smokestacks from where I grew up, where they built the B-24 bomber, a bomber, B-24, every 50 minutes, and the doors didn't fall off. So it's pretty incredible. And this was Ford Motor Company building the B-24s, right? So from the land of Toyota, what were they looking like at the time, 1945, this horrible tragedy in history? This is Hiroshima and Nagasaki, right? So this is the land of Toyota. And they're going to try to compete with this incredible industrial revolution that occurred in Detroit, right? For the most part. So opportunity for Toyota, that's almost laughable when you say it that way. Toyota had produced 2,685 vehicles in 13 years after the war, compared to Ford Rouge plant, 7,000 vehicles a day. Just amazing, right? And they're going to compete with that. So Toyota, from a small island country, dwarfed in size relative to Ford, limited in resource, is positioned to exploit the inherent weakness of mass production and nearly put the arsenal of democracy out of business. Amazing, right? Couldn't believe that would happen. How is it possible? Toyota production system. Or lean manufacturing. Third generation of manufacturing after craft production, job shops, and mass production system. And so currently today, I would say 95% of all manufacturers, including electronic manufacturers, are not operating at a high level of lean. So what's that mean? Tons of opportunity for those who work hard to implement these systems. So, impact on Detroit. 54 years after Hiroshima and Nagasaki, the arsenal of democracy's brought to its knees. Washington Post, January of 2009, Toyota passes GM as world's largest automaker. That is not possible. That makes no logical sense at all, right? How could that be, given that history? And only 4 months later, GM bankruptcy, end of an era. Pretty incredible, right? So that means the audience and those manufacturers out there should understand that this is something we ought to really drive hard, because the opportunity is incredible, what it can do for an organization. And like I say again, if after understanding this history, you don't say we should do this, there's really no hope for you, right? Because it's proven, it's reality, right? So everybody benefits from this greatly, and every organization, including transactional organizations, hospital systems, they all benefit from this. Nobody can say, yeah, but it doesn't apply here. It does. Now, elements of the lean house, right? So I'm going to teach the course in 15 minutes. I'm going to try. So at the foundation is people, team structure. How well have you developed manufacturing teams at the lowest level of your organization, at the process level, that understands every detail of why things fail, right? Have we done that? Standardization. Are standards up to par? Are they well documented? Are they driven? Are they followed? And is there a discipline to standard in the system? Is there leadership there? Or are we cleaning boards with a dirty toothbrush? Right? No excuse for that. But it happens because we don't drive standards. We don't lead standards. We don't improve standards. So we live with what we have. And then the two pillars of lean, Jidoka and just-in-time. Jidoka means quality at the source, in station. Why do we rework? Why do we inspect after it's built? We should question that and drive that as hard as we can, right? And if we do that well, then we have a just-in-time system that maybe at this point that we can put the architecture of just-in-time. Now, I show the continuous improvement method that is strongly linked to people in the system, that they live this life of improvement, that the only reason they go to work is not to build your product. The reason they go to work is to improve your systems. And those people that have the knowledge at the process level are driving that improvement, and they have the authority to make the difference. And the organization grants them the authority to drive so that they can fix your organization. It's where all the knowledge of why all the small things go wrong that need to be solved. And so what are we focused on? Customer. Everything's focused on customer feedback, understanding what the customer wants. We want to delight the customer. And typically in an organization, our primary measures are safety, quality, delivery, cost, and morale. Notice morale. Notice safety. Why? Because we have respect for people and the organizations that build our product. So to talk about the 7 wastes, which is a Taiichi Ohno thing, what he tried to do is say, I want to try to quantify 100% of all the reasons why we're not perfect, right? So in this, if you remember the name Tim Wood, I still use this because I'm old, I got to remember. So transportation, inventory, motion, waiting, overproduction, overprocessing, and defects, right? If you understand what those are, and you're focused on getting those out of your system, and you have a continuous improvement methodology driven by people close to process, you can be great. So this is just an example of an assembly plant, a small example of it. If you notice, the cycle time of the system, 60 seconds. The actual pace at which the customer wants a car is 80 seconds. That's the takt time. Cycle time is somewhat irrelevant, other than that's how we set our system up ideally. And we do that because we have an OEE, overall equipment effectiveness, which is performance times quality times availability. Now, we set our system up, we resource the entire thing to run 25% faster than the customer. That's a lot of waste, right? But it's a reality. We have failure. We have failure in those systems of performance, quality, and availability. So we have to do that, right? So we want to try to challenge that. And if we challenge that, I should mention here, I went too quick. And then we look how we set the jobs up. These are individual jobs through 6 stations. This is non-value added work, which is typically waiting time and poor processing by the industrial engineer or other people that put the operation in place. We also have wait time. They're standing around with nothing to do waiting because it's not well balanced. So there's also waste in how we process the vehicle, even at the 60-second line time. That is why ONO says the number one waste of the 7 wastes is overproduction. You see it right there, right? That's what you're trying to convert. So if we were able to drive OEE from 75% to 90%, guess what? How do we become more profitable as an organization? We slow down. We're working too fast, right? We're overspeeding the customer significantly because of the waste that's inherent in our system. So if we can drive performance, quality, and availability to an OEE at 90%, then we have to farm that waste we put in the system back out. So we move it to 90%. The waste of waiting is reduced. Non-value added work is reduced, and 2 jobs of the 6 jobs are eliminating by combining operations. That's the significance of Toyota Production System mentality and how you drive that with your organization. So we want to move to a just-in-time material pull system, which is very difficult to do, right? So there's other things that have to happen, and you must have repeatability and stability in your system before you do this. Right? So what you essentially want is like a grocery store. Customer takes product, and then you replenish product all the way back to the farm. So it's a system of replenishment. So this, I'm sure many of you have heard of value stream maps. This is just an example of a value stream map. And what we have here is the customer wants 920 parts per day. That's tack time, that's demand, that's sales. We multiply sales, tack time, by the inventory between each process to understand how long it actually takes for a product to flow from order to delivery. And we use tack time because that's the rate at which the customer takes product on the truck away from our facility. We don't use cycle time, right? So in this particular example, there's 7.5 days of inventory sitting there at the customer demand rate. At the end, there's 23.4 days of lead time versus 188 seconds of cycle time. That's not atypical. That's typical. So the job is to remove the inventory as much as possible to reduce the lead time in the system. Now, if you're measuring lead time as an organization, you have teams and they're driven, and you have a continuous improvement system, you can make significant progress here. If you don't measure it and you're not driving it, you probably will never deal with it. And it is the thing that makes lean lean. So just to use a lead time analogy, just for the sake of understanding, let's say this is a highway going from Auburn to Atlanta. 3 hours from point A to point B, or 1.5 hours from point A to point B. The inventory or the cars are what's clogging the system up and making you inflexible and making you unresponsive to customer. And that's what you're trying to drive out. So the reason we don't deal with it is because inventory hides all our problems. Right? We can float on top of the water, we can ignore all the rocks below. Because if we just lower inventory, we're going to crash into the rocks and it's going to be disaster, right? So what do we got to do? We got to get rid of the rocks. That's the continuous improvement. Then we can lower the water, right? So this is Taiichi Ono. He's my hero, right? This is a Henry Ford of Japan. He was responsible for defining the 7 wastes of Muda and also refining the just-in-time material flow that Kanban and other methods. But he was inspired by what? He came over, Henry Ford said, I'll share with you, come over, see our system. He comes over to look at the Ford system, goes back to Japan, and he loved Ford. He thought he was an incredible guy. Still, to his dying day, thought Ford was an amazing guy. But he said, we can't do it. We don't have the capability. It wasn't that he was necessarily a genius, although he was. It was impossible for Toyota to operate the way that Ford Motor Company did. So, but he was mainly inspired by American supermarkets. Wow, customer takes one, and then they replace it, and it goes back to the farm. It's a system of replenishment. I'm going to spend the next 20 years refining a system of replenishment because that can work for us with low volume, high mix in our organization. So he began an effort of creating a supermarket pull system for Toyota, which is what nearly put Detroit out of business. Right. So if the automotive industry globally didn't convert to the Toyota system, they wouldn't be around today. So Ono's definition of lead time is all we are doing, and he speaks in Eastern riddles, so there's a lot being said here. All we are doing is looking at the timeline from the moment the customer gives us an order to the point that we collect cash, and we're reducing the timeline by reducing the non-value added waste. That's what he's saying, right? Reduce lead time. That's the entire Toyota production system. Do we measure lead time? Do we have people and teams that are working to do it? Do we have continuous improvement structures in our system? If we don't do those things, we're missing an opportunity, a great opportunity. So what sequence of implementation would we suggest? Start here. Use the people in your organization, the two tenets of the Toyota production system, respect for people and continuous improvement. Two tenets of the Toyota production system. Start with people. Do you use your people? Are they in work teams? Do they have the authority to drive people above them that have no choice and cannot ignore them to solve the problems at the lowest level? And if they don't, that's a whole nother lecture, but we can talk about that. 2, do you have a continuous improvement system that does listen, respond, and not ignore? Do you have that? No? Another great opportunity. 3, standardization. Can we clean a board properly? Is it properly prescribed? Are people following the standard? Are we leading the standard? Do we ignore deviation to standard or do we address it? Do we have a flexible standard to where we can change it quickly based upon new information? Actually, in an organization, the standard is the control group for experimentation. If you don't have strong standards, you can't experiment. One of Ono's famous quotes was, where there is no standard, there can be no improvement. So standards are critically important, hence they're the foundation of the system. And then Jidoka. Why do we rework? Why do we inspect after the process that actually assembles the product? What can we do to minimize that? Jidoka. Quality at the source. And then finally, if you can get the stability and reliability in your system where it's predictable, you might be able to start implementing pull systems. But without implementing just-in-time pull systems, there's a huge possibility for organizations to make great gains with the first 4. So that's it. I think I meet the time. Thank you.
Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on your favorite podcast app. If you're watching this podcast on the Reliability Matters YouTube channel, be sure to like and subscribe to be notified when new episodes are released. We release new episodes on the 2nd and 4th Tuesday of every month. A very special thanks to the Printed Circuit Engineering Association's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks also for your questions and episode suggestions. Please keep them coming. I love to hear from you. Send comments or episode suggestions to Mike at mikekonrad.com. That's Konrad spelled with a K. To learn more about the podcast, please visit our website at reliabilitymatterspodcast.com. Once again, thanks for listening or watching. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again in 2 weeks. Mahalo.
Thanks for listening to the Reliability Matters podcast. Join us on the 2nd and 4th Tuesday of each month for new episodes of Reliability Matters.